Watch a student memorize a formula, pass a test, and then encounter a real-world problem. When the gymnast hits the mat, the textbook equation vanishes. In a study of 8th grade physics students, researchers examined how children learned the mechanics of density, speed, and force. One group followed the traditional tell and practice model, receiving formulas like density equals mass over volume up front. The second group received no formulas. Instead, they were asked to invent their own mathematical procedures to characterize the physical phenomena. Weeks later, both groups faced a novel transfer task. Using these diagrams, they determined fabric stiffness based on how far the mat stretched under the weight of several people. The students who invented their own math were 4 times more likely to successfully utilize ratio structures than those taught with conventional formulas. Memorizing an abstract equation does not ensure conceptual understanding. To find out why the invent group outperformed their peers so significantly, we have to look at the gap between what we see and what we calculate. Traditional instructional design assumes a direct one-to-one mapping between a physical object and a mathematical symbol. It treats the symbol as a simple label for a concept the student already perceives. This assumes the mapping is automatic. But a different framework, known as the coevolution hypothesis, suggests a more complex relationship. Coevolution posits that our understanding of concrete materials and abstract symbols develops in tandem, with each psychological advantage building on the other. Engineering true transfer requires us to examine the specific ways novices misperceive physical objects before they ever touch a formula. We need to see if mathematical understanding is a matter of stripping away physical details, or if it requires a different kind of interaction between these two cognitive domains. Curriculum designers often fall for the illusion of isomorphism. They assume students automatically see the same mathematical structures in a classroom manipulative that an expert does. To see this in action, researchers tested this exact phenomenon with a group of 4th graders who were just on the cusp of understanding fractions. Look at the right side of this display. Children were shown 8 pieces pre-grouped into pairs and asked to identify 1/4 of the set. Despite the grouping, students fixated on the numbers 1 and 4. They circled exactly 1 chip, 4 chips, or both. They relied on their most practiced cognitive schema, natural numbers. This prior knowledge blinded them to the intended ratio, even when the physical objects were literally grouped to show it. The students noticed the surface features, the individual chips, but could not see the deep structure of the mathematical ratio. As it turns out, merely handling physical materials is just not enough to force the developing brain to automatically perceive a novel mathematical relationship. If physical objects aren't enough on their own, what mechanism allows a student to finally see that deep structure? Another experiment used balance scales to see how 8 to 10-year-olds predict tipping points. In one condition, researchers used beakers of liquid. In another, they used weights on evenly spaced pegs, easily turning physical properties into numbers. One group justified predictions using words, like the left side has more. The other invented mathematical justifications using symbols. The words-only group failed. They fixated on a single dimension, either the weight or the distance, but they couldn't coordinate both. But the group inventing math succeeded. Using symbols allowed them to hold weight and distance in their mind simultaneously until they discovered the multiplicative relationship. Symbolic notations provide a compact way to combine perceptually distinct dimensions. They allow the brain to test candidate operations, like multiplication, that are difficult to perform through pure observation. Many classrooms use the symbolic to concrete approach. The teacher explains the formula first, and students then apply it to physical examples. To test this, researchers gave middle schoolers a worksheet designed to teach the concept of density. This worksheet describes companies shipping clowns and buses. It's filled with surface features, clown illustrations and graphics irrelevant to the math. But the deep structure is hidden in the ratios. The first company uses different-sized buses, but always maintains 1 clown per compartment. In the tell and practice group, students were given the density formula, mass over volume, before they started. They used it to quickly calculate the answers for each bus. A day later, students were asked to redraw the worksheet from memory. The group given the formula remembered the surface details, but they failed to recreate the deep structural ratios. Because these students had the formula up front, they could mechanically solve the problems without ever actually looking for the structural patterns in the buses. Providing the symbolic method before the exploration prevents the brain from encoding the structure of the physical situation. Students learn to apply a rule, but they never learn to see the pattern that makes the rule necessary. If giving formulas too early prevents learning, we need a different model, inventing to prepare for learning, or IPL. IPL relies on contrasting cases. Look at these 4 grids showing where different pitching machines landing their balls. Placing them side by side forces the brain to notice structural variations. You see the difference between inaccuracy, distance from the center, and variability, how tightly they cluster. Students are then asked to invent a single mathematical index that can characterize the reliability of every machine on the page. This demand for a precise symbolic account forces the student to quantify the exact magnitude of the structure they've noticed in the grids. IPL creates a synergy where physical observation bounds the symbols we create, and those symbols, in turn, sharpen what we see in the physical world. This brings us back to the trampoline test. The goal was to find a way to describe the stiffness of the mat fabric. The Invent group succeeded because they spent their density lesson building a rule relating clowns to compartments. Having an agile understanding of ratio, they saw the relationship between a load and a mat stretch was fundamentally the same structure. The Tell and Practice group failed, possessing only a formula for density. Without the prompt D equals M over V, they didn't know which rule to apply. Generalization depends on learning to perceive invariance, the structural properties that remain constant even when the surface details change. The coevolution hypothesis suggests that if we want students to move beyond memorization, we must change how they interact with symbols and objects. To build minds capable of transfer, we have to stop giving students the answers at the start. Instead, we must engineer environments that challenge them to invent the structures for themselves.